Thank you, Dr. Roshni. Good evening, everyone. As Madam informed, I'm Ramgopal. I'm from the Department of Mechanical Engineering, IIT Kharagpur. Today, I'll be speaking about design and development of CO2-based secondary loop systems for cold storage applications. This work was carried out under a sponsored project funded jointly by ISHRAE and SCRB TST. So before I actually discuss about this particular project, I would like to give a brief background. This is the overview of the presentation. I'll just quickly explain about secondary loops and why do we need secondary loops in refrigeration. And then in this particular system, we have used CO2, carbon dioxide, as a secondary fluid. So what are the advantages of carbon dioxide in comparison to the other fluids? And what are the potential applications of CO2-based natural circulation loops? And then some studies, we have been working on these CO2-based loops quite for some time. So I would like to mention very briefly some of the studies carried out at IIT Kharagpur on these systems. Then I'll briefly mention about CO2-based secondary loop systems for cold storage applications, and then their relevance with reference to low ammonia charge systems. And then finally, I'll discuss about the SCRB ISHRAE funded project and what we have done under this project and what are the research highlights. And finally, what are the practical problems to be resolved. So I'm sure all of you know that a closed loop is nothing but a loop in which a circulating fluid transports heat from the heat source to heat sink. The circulating fluid typically is called as the secondary fluid. So as the secondary fluid circulates through the loop and carries heat from the heat source to the heat sink, it may or may not undergo phase change. That means it may remain as a single phase fluid, or it may get converted into two phase as it picks up heat or rejects heat. So, I mean, the secondary loops are quite widely used in air conditioning systems and refrigeration systems. And in these loops, water and brines are the most widely used secondary fluids. For example, all large air conditioning systems, we use water for transferring heat from the conditioned space to the refrigeration plant. And in many industrial refrigeration systems, brines are used when we require low temperatures, lower than 0 degrees centigrade. So secondary loops are very well known. Generally, most of the secondary loops that we use in industry and in air conditioning and all, they are forced circulation type. That means we typically use a pump for circulating the fluid. We can also use buoyancy and circulate the fluid through natural circulation, in which case we do not require any pump. For example, this is a typical simple schematic of a forced circulation type secondary loop. You can see that a pump is there. The pump consumes some little amount of power for overcoming the friction, and then we have a heat source where heat is given, and heat sink where the heat is transported to some other system. So even though this figure shows that it is a vertical loop, this is independent of the orientation. That means this system can be oriented in any way. So as again as this, we have natural circulation loops. For example, this is a small natural circulation loop which is used for electronic chip cooling. Here you can see that we have a hot chip and a cooler, and there is no pump. So here the circulation is only due to gravity and by density difference. So here the orientation is important. You have to keep it vertical so that due to buoyancy the fluid circulates. So why do we need secondary loops in refrigeration? So all of you again know about global warming and what are the problems with many of the synthetic refrigerants that we use in refrigeration. Most of the synthetic refrigerants that were used and that are being used have high global warming potential. So eventually we may have to phase them out by some other refrigerants which have low GWP. There are many regulations on high global warming potential synthetic refrigerants. So we have to look for other fluids. In fact, if you do the analysis, you will find that the impact of refrigerant, direct impact of refrigerant is global warming, is many a time much less than its indirect effect. Indirect effect means through its efficiency. So we require not only low global warming potential refrigerant, but we also require a refrigerant which gives rise to high energy efficiency. So we require low global warming potential, and high energy efficient refrigerants. So if you consider these criteria, we realize that many of the natural refrigerants, such as ammonia and hydrocarbon, are ideal because they not only have very low global warming potential, but they also offer very high energy efficiency, apart from many other advantages. So gradually, people are realizing that instead of using synthetic refrigerants, it would be good in the long run if you go for natural refrigerants, mainly ammonia, hydrocarbons, water, carbon dioxide, etc. So out of these, ammonia is most widely used, as all of you know, and hydrocarbons are also used in many refrigeration systems. But the problem with these two refrigerants is that they are toxic. For example, ammonia is toxic and flammable, and hydrocarbons are highly flammable. So when we use ammonia and hydrocarbons in refrigeration systems in large quantities, then it gives rise to safety concerns. We have to design and operate the systems in such a way that it doesn't create any safety problems. So if you want to really you use them on for many applications, then we have to take care of the safety problems through safe designs. So there are many ways by which you can improve the safety aspects of ammonia or hydrocarbon refrigerants. So one of them is the use of secondary loops. By using the secondary loops, what we can do is we can reduce the amount of refrigerant required for a given capacity, and we can confine the refrigeration system through which these flammable or toxic refrigerants are circulating to plant rooms. We need not bring them to the conditioned space, so we can confine them to the plant rooms. Thereby, we can improve the safety to a large extent. So next comes, as I already mentioned, we use water and brines very commonly as secondary loop fluids. But why are we talking about carbon dioxide? So carbon dioxide, this is the phase diagram of carbon dioxide. I'm sure you are familiar with this. So carbon dioxide has several interesting characteristics. For example, it is non-toxic and non-flammable. So unlike ammonia and hydrocarbons, it is very safe, and it has a zero ozone depletion potential, so there is no problem from ozone depletion point of view, and its global warming potential is very low. It's one, and it has excellent thermophysical properties. It has very low viscosity, very good thermal conductivity, and other very favorable thermophysical properties. And it has excellent material compatibility, so you don't have to really go for any special materials. And it is obviously abundantly available. And it is since it is abundantly available, it is a very low cost refrigerant. Okay. One important characteristic of carbon dioxide is that it has a relatively low critical temperature when we compare it with other refrigerants. For example, its critical temperature is 31 degrees and critical pressure is around 74 bar. So this gives rise to many challenges and also many opportunities. We'll see that later. So what is the advantage of CO2 as a secondary fluid? Because of its favorable properties, thermophysical properties and other properties, it is gaining actually popularity as primary as well as a secondary refrigerant. There are many vapor compression refrigeration systems where carbon dioxide is used as a primary refrigerant. They can be subcritical or transcritical or in cascade, etc. So they are now being promoted on a large scale. Carbon dioxide can also be used as a secondary refrigerant or a secondary fluid. So as I mentioned, systems that use carbon dioxide as primary refrigerant are already in market. Many countries are marketing these things, mainly in Europe and to some extent in Japan. So the other potential application, so primary refrigerant is being established, but CO2 can also be an excellent secondary fluid, particularly for cold storages and supermarkets, because in cold storages we use ammonia in large quantities, and in supermarkets we want to use some refrigerant which is neither toxic nor flammable. So under these circumstances, one can think of a secondary loop system with CO2 as a secondary fluid and using hydrocarbon or ammonia as a primary refrigerant. So what is the advantage of CO2? I mean, why not water or brines? So the analysis shows that if you are using CO2 as a secondary fluid, our loops will be very compact. And we can also reduce the pumping power to a great extent. So this is a major advantage of CO2 as a secondary fluid in comparison to other fluids like brines and all. So you have very compact loop, and with much less pumping power. Of course, the one major problem with carbon dioxide is its operating pressures are relatively very high, at least one order of magnitude higher than the other fluids. So this is one issue that needs to be taken care of when we are designing these systems. And as I mentioned, since it has low critical temperature, it is not possible to operate in a subcritical cycle mode when your heat sink temperature is high. If I am talking about a use of CO2 as a primary refrigerant. So this gives rise to what we call as a transcritical vapor compression refrigerant systems, where the condenser is replaced by a gas cooler, because you cannot condense carbon dioxide when the sink temperature is above 31 degrees. Okay, so this is the challenge that we need to handle when we are using it as a primary refrigerant. Of course, we do not have the problem of the critical temperature most of the time when we are using it as a secondary refrigerant in refrigeration applications, because in that case we'll be operating in subcritical mode, but still the high pressures are high. So the high pressures have to be taken care of through proper design and operation. So CO2 based, so coming to, I'm not going to discuss about the use of CO2 as a primary refrigerant. That is not the topic of this. So we are mainly interested in CO2 as a secondary fluid. So I'll be focusing on that. So the CO2 based secondary loops can be forced circulation type or natural circulation type. In forced circulation type, as I already mentioned, a pump is required for circulating the fluid, whereas in natural circulation, we'll be using gravity for circulation. And the secondary loop can fluid can undergo phase change or without phase change. If you are using it for high temperature applications, then the loop will be in gaseous phase, so in a supercritical condition. But if I am talking about low temperature applications, then it may be in two phase, liquid and vapor. And there are companies offering the use of CO2 as a secondary fluid in many applications, as I said, in supermarkets, cold storage, etc. For example, these are the famous companies like Maekawa from Japan, Danfoss, Emerson, and Sheco. These are the companies which are offering refrigeration systems where CO2 is used as a secondary fluid in forced circulation mode. That means using a pump. However, as far as I know, there are no commercial systems where CO2 is used in natural circulation mode. So this is what makes it interesting, and this is the major research gap that needs to be addressed. So just for the sake of comparison, let us quickly look at forced circulation versus natural circulation. What I am showing here is a forced circulation type loop, where ammonia is used as a primary refrigerant. This component is called as a cascade condenser, where carbon dioxide vapor condenses by rejecting heat to ammonia. And this condensed carbon dioxide liquid, which is at low temperature, is pumped through an evaporator, a carbon dioxide evaporator or air cooler, where it becomes vapor by extracting heat from the air. So in this process, air gets cooled, and the liquid carbon dioxide gets converted into vapor. So the vapor goes back to the cascade condenser, where again it rejects heat to the ammonia, and it becomes a condenser, and the loop continues. So this kind of systems can be used in cold storages and supermarkets, where the ammonia doesn't come into the conditioned space. In the conditioned space, we have to keep the air cooler through which the carbon dioxide only flows. So what are the advantages of forced circulation type loops? So forced circulation type of loop is independent of orientation. So it is not, it can be horizontal, it can be reversed, the cascade condenser can be at the bottom and evaporator can be at the top, etc. So it gives a lot of flexibility in terms of arrangement. And they can also be made very compact, because since we are using a pump, I can afford to have a slightly higher pressure drop. So thereby I can use higher velocities. If I'm using higher velocities, I can reduce the pipe size and I can make the entire system quite compact. So this is another major advantage of forced circulation type loop. And it has a faster response time, because the moment you switch on the pump, the system starts working. So it starts very quickly, and it can also be stopped very quickly. And there are no instabilities. So we'll see, I'll discuss about instability when I talk about the natural circulation loop. So these are the major advantages of the forced circulation type loops. But they have some disadvantages. The major disadvantage is you have a pump. A pump has moving parts. So whenever you have a device having moving parts, it is less reliable. The pump can fail. So this is a major problem. And obviously the pump requires some power. This the power consumed by the pump will be added to the refrigeration capacity. So this is a loss of refrigeration. In addition, you also have to provide an additional power. So this is a disadvantage. And it is very difficult to maintain a very uniform flow when I'm using a header and I'm distributing the two-phase into different parallel pipes. Using force circulation, it is very difficult to have uniform distribution. That means the vapor and liquid fraction through each parallel tube may not be same. So this is one major challenge when we are using force circulation in two-phase flows. So these are the disadvantages of force circulation now. So when it comes to natural circulation, you can see that it is almost similar. The only difference is that we don't have a pump. So since we don't have a pump, we have to keep the cold component, that means the cascade condenser, at an elevation compared to the hot component, that is your air cooler. The air cooler is the one where you are supplying heat, so it has to be at a lower level, and where I am cooling carbon dioxide has to be at a higher level. So it creates a buoyancy head, and since the liquid is denser than the two-phase mixer or the vapor, so the liquid comes down and vapor moves up, goes up. So as long as you are supplying heat in the air cooler, there will be continuous circulation of carbon dioxide. Okay, so but for this I have to have gravity, and I have to maintain certain level difference so that the required amount of carbon dioxide can flow. So what are the advantages of this kind of loops? So they are very reliable because I'm not using any pump. So there is no question of any failure as far as the carbon dioxide loop is concerned. And obviously, there is no pump, there will be no pumping power requirement. And studies show that when you have natural circulation and two-phase flows, the distribution of two phases are more uniform. So this is one inherent advantage of two-phase natural circulation loops. Obviously, it has some disadvantages. The disadvantages are the orientation is restricted, and I have to have certain amount of height for the system to operate. So this is one of the major disadvantages of natural circulation loop. And there is also a possibility of flow instability. That means depending upon the design and all, if it is not properly designed or properly operated, the flow can reverse. That means in this diagram, the flow is clockwise. So it may so happen that instead of clockwise, due to flow instability, it may flow in anti-clockwise direction for some time, and again it can switch to clockwise. So this kind of instabilities can occur depending upon the operating conditions and the design. So this is one problem that needs to be taken care of when we are designing natural circulation loops. So these are the advantages and disadvantages of both forced circulation and natural circulation. So this is just an example of what is the advantage that you get if you are using carbon dioxide. This figure is taken from the Mayakawa. You can see that it's a 2008 publication from Mayakawa. Here, this consists of, this is actually a system where ammonia is used as the primary refrigerant and carbon dioxide is used as a secondary fluid in a forced circulation loop. This is a forced circulation loop. So you can see that there is a pump here. Okay. So what I want to mention, or what the company wants to highlight, is that the reduced size of the pipes. So you can see that if I'm using brine, the bottom, the pipe sizes are pretty large. I have to use either DN125 or DN150 for the supply or the return pipes. But if I'm using copper pipes, I can use DN65 for both return and supply. So the system becomes very compact. So this is because of the favorable thermophysical properties and high pressure operation of the carbon dioxide. So this is apparent if you just look at the properties. I'll quickly go through it. So you can see what the figures, what I'm showing is a comparison between different properties which are of importance in natural circulation loops. So these are the properties of the saturation liquid. So on the x-axis I have temperature, and the first figure, what is shown on the y-axis is the coefficient of thermal expansion. This property is very important for natural circulation loops because this is an indication of the buoyancy that we can generate for a given temperature difference. So several liquids are compared here at different temperatures. So here you can see that carbon dioxide has the highest coefficient of thermal expansion. That means for a small temperature difference, it can generate a large buoyancy force if I'm using carbon dioxide. So there will be excellent circulation. Okay. Or in other words, for the same flow rate and all, the required elevation can be reduced if I'm using carbon dioxide. So this is an advantage in comparison to all other fluids. Okay. And again, you can see the density of carbon dioxide is reasonably high in comparison to many of the refrigerants. So high density also will give rise to compact loops. So this is another advantage. Another very important advantage is viscosity. So you can see that among the different secondary fluids considered here, carbon dioxide has the lowest viscosity. Right? You can see that the bottom curve is for carbon dioxide. All other secondary fluids have higher viscosity. So low viscosity means again compact loops, lower head required, etc. So these are the important properties, and from these properties, one can say that carbon dioxide can be a very good candidate for secondary circulation loops. And this is again a small comparison between the diameter ratio as a function of temperature for different fluids. The first figure shows the diameter of the fluid used to the diameter of carbon dioxide. So if the ratio is 1 means the diameters are same. That means carbon dioxide tube diameter and the fluid diameter is same. And if it is greater than 1 means any other fluid requires a diameter which is larger than the carbon dioxide. So you can see that for most of the temperature range considered, all other fluids, the diameter ratio is more than 1. Okay, this means that your pipe size will be much larger if you are using any other fluids other than carbon dioxide. The same thing you can also see the area ratio. Again, you see that the area, in terms of the area ratio, you require very high areas if you are using fluids other than carbon dioxide, because the area ratios are much higher than 1 for most of the fluids. Again, it means that if I'm using carbon dioxide as a secondary fluid, my loops will be very compact. So this can be a very important advantage, because there are also some studies where people wanted to use carbon dioxide in automobile air conditioning. So in automobile air conditioning, they wanted to use a secondary loop fluid, and carbon dioxide is supposed to be the secondary fluid, and the primary fluid will be hydrocarbon, which will not be kept inside the cabin. It will be away from the passenger cabin, and only carbon dioxide will be circulating through the cabin. So in that case, compactness is very important. So carbon dioxide can be a very good candidate for that. So what are the potential applications of carbon dioxide based natural circulation loop? There are many applications. This is very interesting study. This was actually carried out way back in 2008 in Japan. So this is actually a small air conditioning system where isobutane is used as the primary refrigerant, and carbon dioxide is used as a secondary fluid in natural circulation. You can see that there is a carbon dioxide evaporator or the air cooler, which is at the bottom of the unit. The top part of the unit, which consists of the condenser, the compressor, and the heat exchanger, isobutane carbon dioxide heat exchanger, all these things are kept outside the room, and only this CO2 evaporator is projects into the room, and air circulates over the CO2 evaporator, and air gets cooled and dehumidified. And in this process, carbon dioxide becomes a vapor. That carbon dioxide vapor goes to the heat exchanger, where in the heat exchanger it rejects heat to isobutane, and it becomes a liquid, and the liquid again comes back to the evaporator. And the isobutane, as it picks up heat from the carbon dioxide, becomes a vapor. It goes into the compressor, it gets compressed, and from there it goes to the condenser, and then through the expansion valve, and the cycle continues. Okay, so this is a very interesting, very early example of use of carbon dioxide as a secondary fluid using natural circulation. So carbon dioxide can very well be used in small cold storages in natural circulation loop. For example, here if I have a cold storage where I want to use ammonia as the primary refrigerant, but I don't want to bring ammonia into the cold storage, I can keep the ammonia out of the system. So this is my ammonia unit, which is kept above the cold storage or away from the cold storage, and the heat is transferred from the cold storage to the evaporator of ammonia by using a secondary loop. So you can see that is a natural circulation loop through which carbon dioxide will be circulating. So this is the air cooler through which carbon dioxide will circulate and extracts heat from the air. Okay, and the carbon dioxide vapor, because of the low density, it flows up and it flows through the evaporator, becomes liquid and comes down. Okay, so this circulation can be maintained as well as long as I'm supplying heat here and I have the required height difference. Okay, so this I've already explained to you, so I will go into this. This is another potential application, which is of course not yet evaluated. You are aware of the domestic refrigerators, typically a two-door refrigerator where we keep the freezer at the top and the fresh food compartment at the bottom. Normally, a freezer is maintained at about -18 degrees and the fresh food at about +2 degrees. And most of the small systems have a single evaporator and a single compressor. The evaporator, which will be operating at very low temperature, is typically kept in the freezer compartment. So what we do is we cool the air to very low temperatures, and a small part of that very low temperature air is circulated through the fresh food compartment, and a large portion of it, the remaining portion, is circulated through the freezer. Right. So what we are doing here is we are supplying air at very low temperature, maybe -20 degrees or so, into the fresh food compartment, which is maintained at +2 degrees. So even though I require only +2 degrees, but because I am using a single evaporator, I have to cool all the air to -20 degrees centigrade. So studies, you can show that this is not very efficient system because you are unnecessarily cooling to very low temperatures for the fresh food compartment. So the proposal is that instead of circulating air through these two compartments and mixing them, you can separate these two compartments and you can use a CO2-based secondary loop. So in the CO2-based secondary loop, CO2 will be circulating through the roll bond evaporator. It picks up heat from the fresh food compartment and becomes vapor, and vapor goes into the evaporator and it again becomes liquid and liquid comes down. So this circulation is maintained because of the height difference and because of the heat transfer. And in this system, the freezer and fresh food compartments are truly isolated. So there is no mixing of air of the fresh food compartment and freezer compartment. Sometimes this can be a big advantage in domestic refrigerators because if you are mixing air, there will be transfer of odor from one compartment to the other compartment. So this is one of the typical problems in domestic refrigerators. Suppose I am keeping fish in freezer and some vegetables or fruits in fresh food compartment. Because of the circulation of air, you may transfer the fish odor from the freezer to the fresh food compartment. So this is one practical problem. In addition to that, in this kind of a conventional system, when air is mixed, a large amount of moisture is also transferred from the fresh food compartment to the freezer compartment. So this gives rise to frosting of the evaporator, which is not good. Right? These problems can be taken care of by isolating them and by connecting them using only a secondary loop using carbon dioxide. Okay, this is just a concept; it is not yet evaluated, but this is an interesting possibility. Of course, this is another application of carbon dioxide natural circulation loop type solar collector, where carbon dioxide is a working fluid. All of us are familiar with flat plate solar collectors, or in flat plate solar collectors, typically small solar collectors. We don't use a pump. The circulation is because of again the density difference. So the hot water tank is kept at a higher level. And the water at the cold water enters at the bottom, and as it is cold, its density is high, so it circulates through the collector, okay, and gets heated up and it circulates. So this kind of systems are very widely used, but there are places where we cannot use water directly, because if the temperature goes below 0 degrees centigrade during night, then there is a possibility of water freezing in the solar collector. So in that case, we have to use an indirect type solar collector. In an indirect type solar collector, we use a fluid which is different from water in the solar collector. That means, suppose I am using a heat exchanger. Okay. So here there is no mixing of water with the fluid which is circulating in the solar collector. So we can use carbon dioxide as the circulating fluid in the solar collector, and this hot carbon dioxide transfers heat to the water through this heat exchanger, which is immersed in the hot water storage tank. So the advantage of using carbon dioxide is, again, you can have very highly efficient heat transfer. As a result, your solar collector efficiency can be increased because you can produce hot water without heating the plate too much. So thereby you can reduce the losses. So this is one of the potential applications of carbon dioxide in a natural circulation loop. There are some studies and some research results are available on this kind of solar collectors. So these are some of the applications of natural circulation loops, and especially with carbon dioxide as the loop fluid. Now let me quickly go through some of the studies that we carried out at IIT Kharagpur. So we have over the years, last maybe 15 years or so, many of our students have carried out research on these systems. A large number of theoretical studies are carried out, steady state, transient modeling. We have considered all kinds of loops, single phase loops, two phase loops, and transcritical, supercritical loops, etc. Our students have developed many simulation models using a variety of packages, Fluent, MATLAB, etc. And we also carried out a large number of experimental studies, and these experimental studies are carried out on subcritical CO2-based systems for low temperature applications. We also carried out studies on two-phase carbon dioxide loops. And we also carried out studies on supercritical CO2 loops for high temperature applications. So all these systems are built and operated. They are still running in our laboratory. This is one of the first studies carried out by one of our students. This is where actually, of course, we did not build the entire system, but here we have combined the carbon dioxide based natural circulation loop with an air conditioning system. In those days, we considered R22 as the refrigerant just because it was available in those days. So you can see that the evaporator of R22 is combined with a condenser of carbon dioxide. So, and this hot heat exchanger or the cooling unit is supposed to be kept in the conditioned space, and all other components are kept away from the conditioned space. Okay, and this is the typical phase diagram of carbon dioxide and R22. So a large number of studies are carried out on this system, mainly simulation studies, and we also built a small experimental setup. One point we have to keep in mind is whenever we are introducing a secondary fluid, I'm introducing an additional resistance for heat transfer. Because if there is no secondary fluid, there is a direct heat exchange between the primary refrigerant and the air, or the primary refrigerant and the conditioned space. Now I am introducing a secondary loop, thereby I am introducing an additional resistance. So this additional resistance theoretically will reduce the overall energy efficiency of the system to some extent because of the increased resistance. So the challenge is to maintain the performance without losing the efficiency, at the same time introduce a secondary loop. So this is a major issue whenever we are using a secondary loop in any refrigeration system. For example, this result from the simulation show that in the first graph for different space temperatures and space relative humidity, we have seen what happens when you are introducing a secondary loop. How does it compare with the base loop? Base system. Base system means we do not have any secondary loop. Directly the R22 is cooling the air. Okay. So you can see that the moment I introduce a secondary loop in the form of a carbon dioxide loop, there is a small loss in capacity and a small loss in COP. Of course, the capacity loss and COP loss is less than 10%. And if you are talking about higher temperatures, the loss is very low. The loss is slightly higher at low temperatures, at about 8 to 7 to 8%. So this is something we need to take care of. Obviously, these results are based on many assumptions. So when we are actually designing the system, the difference may be much less than what we are showing here, because when I am introducing a secondary loop, the amount of refrigerant used can be reduced, and the pipeline length can be reduced to a great extent. So because of this, for the primary refrigerant side, the performance can be improved. So thereby, the difference between the base system and the secondary loop system can be reduced, okay, with through proper design. So this is the first study that we have done, and this study shows that it is technically feasible to introduce a secondary loop. And then we have built a small system. You can see that the bottom one is a two-phase evaporator where carbon dioxide, liquid and vapor mixture will be flowing. And heat is supplied here. It moves up through this vertical tube and it flows through this condenser at the top. So in the condenser, it loses heat to water, which circulates through this, and it becomes a liquid, and liquid comes down. So a large number of experimental studies were carried out just to validate the mathematical models, etc. Then we also made a small system. This is called the mini loop system. This system was used to evaluate our CFD codes. So our student has developed a large number of CFD codes to study two-phase, single-phase, and transcritical or supercritical loops. So to validate those things, we have built this small loop. This loop is made small, and we wanted to see the effect of the orientation. So it is a tiltable. You can tilt this loop in any direction, and we can see what happens when you are tilting it, how the system performs. Okay. And then we also made a, so the previous two examples, the heat exchangers used are tube-in-tube type heat exchangers, and the external fluid used is liquid. That means water is used as external fluid. So in this study, we have used a air to carbon dioxide heat exchanger on one side and an electrical heater on the bottom. So this kind of systems find application in high temperature supercritical applications. On a very small scale, such systems may be used for cooling of electronic chips, or on a large scale, we can use these systems for geothermal heating, nuclear power extraction, etc. So the high temperature CO2 loops also have large number of applications. So we have built a small system to study the performance of this under high temperature conditions. So again, this is a small setup built. The setup is pretty simple because it's a natural circulation loop. You don't require any pump or anything. You require some pipelines and heat exchangers. So here we have at the bottom, we have a heat source, and at the top, we have a fin and tube type of heat exchanger, which is kept inside a duct, and air flows over through this duct, and it gets heated up as it extracts heat from the carbon dioxide. Carbon dioxide is heated at the bottom and it circulates. Okay. One thing you have to remember is these are all high pressure operation. The pressure may be typically it's supercritical, so pressure may be 100 bar or even more. Okay, so this has to be taken care through proper design. Now coming to the CO2-based secondary loop systems for cold storage applications. Again, this is very well known to all of you. So in India and many countries, ammonia is the most widely used refrigerant for cold storage applications. The reasons are obvious. Ammonia is very low cost and easily available refrigerant, and it is an excellent refrigerant as far as the performance is concerned. So we get both economic and energy benefits if I'm using ammonia. So it is used widely all over the world. Unfortunately, conventional cold storages, the old cold storages which we see for the storage of potatoes, etc., we find that a large amount of ammonia is used in these systems, because in these systems the focus is not really reducing the amount of ammonia, but for some other practical reasons. They use large amount of ammonia. So as a result, these systems can become very dangerous if there is any refrigerant leakage, because we may be using thousands of kilograms of ammonia in these cold storages. So if there is a leakage, it can create a huge panic, and it may lead to loss of products, because ammonia, if there is any leakage into the conditioned space, ammonia will leak into the cold storage, so the products may get spoiled. And ammonia, if it leaks out, then it will create problem on the surroundings, and it may even lead to loss of life. So these are serious problem. And accidents involving ammonia leakage are not very uncommon. Even once in a while, you read in newspaper that there is a leakage in some cold storage. Okay, for example, this is just clippings from this publication. You can see that this is a US paper, so you can see what are the effects of these leakages. You can see that the effect is people falling sick to people dying. Right? So this is a very serious problem. So that is one of the reasons why people are afraid of using ammonia. So one has to be very, very careful when we are handling ammonia. Okay. So ammonia, again, just for the general information, ammonia, as all of us know, exists as a gas at normal temperature and pressure. So it is colorless, lighter than air, and it's highly reactive. This is another problem. One good thing of ammonia is it has a very pungent smell. We know from our school labs that if ammonia leaks, we can immediately detect, because our nose is very sensitive to ammonia. So we can detect it at concentrations as low as 5 ppm. Ammonia is not only toxic, it also forms a flammable mixture. So this is your lower flammability limit and upper flammability limit. So what happens if the ammonia concentration increases? If the concentration is around 5 ppm, this is the order threshold. That means we can begin smelling ammonia, we can start detecting. Our nose starts detecting, and if the concentration is between 100 to 200 ppm, then our eyes starts watering and you have irritation in eyes. And if it becomes 400 ppm, then you'll have throat irritation. And if it is greater than 400, below 500, you may have problems to your eyes and your, but there may not be a permanent damage. And if it is 1700 ppm, you'll start having breathing problems, coughing and all. And if it is 2400 ppm, and if you are in that environment for 30 minutes or more, then it may become fatal. And if it exceeds 5000 ppm, or if a pure liquid comes in contact with our skin, then it can burn the skin and it can be very dangerous. So you can see that the concentration has to be kept very low. So this means that the leakage has to be taken care of, and we also have to minimize the amount of ammonia used. So as a result, people nowadays people talk about low ammonia charge systems, because we want to use ammonia as much as possible, because ammonia has all other advantages and it's an excellent refrigerant. And probably you know that this is the only refrigerant which is used continuously over the last 150 years. It was never stopped. Many other refrigerants like carbon dioxide, hydrocarbons were stopped for several decades due to some other reasons. But ammonia, in spite of its flammability, toxicity, etc., it has been in use continuously because of its other excellent properties, which really dominate the toxicity and flammability issues. And if possible, we would like to use ammonia as much as possible, because its global warming potential is zero, and it doesn't have any ozone depletion potential. So it is environmentally, it's excellent fluid. Okay. But provided we improve its safety aspects. So the safety aspects can be improved by reducing the amount of ammonia used, or what you call as the low ammonia charge systems. Of course, there are various ways of reducing the ammonia charge. For example, your International Association for Cold Storage Construction, they classify the low ammonia charge systems into these following three types. The first type is you have a conventional system, but you optimize the conventional system. How do you optimize the conventional system? You redesign the heat exchangers and you make them very compact, so that the amount of refrigerant that gets stored in these heat exchangers can be reduced to a large extent. For example, instead of using flooded evaporators and all, one can think of using a direct expansion type evaporator, so you can reduce the amount of ammonia. And you can also reduce the amount of ammonia by using electronic expansion valves and other controls, so that you can reduce the receiver volume, right? So thereby you can reduce the amount of ammonia required to a great extent. So this is one of the most popular ways of reducing ammonia. The other one is use rooftop package systems in place of central systems. In a typical cold storage, we use a central system where the plant is located, generally slightly away from the cold storage. So you have to transfer ammonia from the plant to the cold storage using big pipelines. So these pipes consist of large amount of ammonia. So these pipeline, ammonia stored in the pipelines can be reduced to a great extent if, instead of using a central system, if I'm using a rooftop package system. Okay, so the system is directly mounted on the roof, so the pipeline lengths are reduced to a great extent. The third one is obviously a hybrid system, what I am talking about. So there we can use, again, there are different types of hybrid systems. For example, I can use a hybrid system in the form of a cascade. That means I'll be using two vapor compression refrigerant systems. On the low temperature side, I can use a carbon dioxide based compression system, and on the high temperature side, ammonia. So by using these systems, I can reduce the amount of ammonia, and I can keep ammonia away from the storage space. Or the other type of hybrid is that to use to use carbon dioxide as a secondary fluid, what I have described so far. So these are the three popular ways by which you can reduce ammonia, and you can develop the so-called low charge ammonia systems. You can also think of a combination of all these things. By using the combination of all these things, in fact, the amount of ammonia that is required has been reduced to a great extent. I mean, nowadays the amount of ammonia used is a small fraction of what we normally used to use in conventional systems. Okay, and this is just an example of a conventional cold storage. In a conventional cold storage, you can see that ammonia evaporator is kept inside the cold storage, and the condensing unit or the compressor, condensers, etc., are kept away from the plant. So ammonia has to transfer or flow from the conditions placed through the refrigeration plant through these pipelines. So the amount of ammonia required will be very high. And I'm also bringing ammonia into the conditioned space. Okay. So this is the cascade system. What in the cascade system, what we are doing is we are hybridizing a carbon dioxide based vapor compression system with an ammonia based vapor compression system using a cascade condenser. You can see that this is a cascade condenser. In a cascade condenser, carbon dioxide vapor condenses and ammonia liquid boils. Okay, so you have a simultaneously condensation and boiling happening in the cascade condenser. So the cascade condenser and carbon dioxide compressor, ammonia condenser, everything, they are kept in the plant room away from the conditioned space. And the pipelines carry now only carbon dioxide. So we can reduce ammonia to a great extent. And again, I'm not bringing any ammonia into the conditioned space. So the conditioned space is safe. So this is the one which I mentioned. This is a 4 circulation type system where carbon dioxide is used as secondary fluid, and the secondary fluid transports heat from the cold storage, which is maintained at about 2 degrees or so, to the refrigeration plant, which rejects heat to the surroundings, which may be at about 35 degrees or so. So again, this is here I'm not using a compressor, but I'm using a pump for circulating the carbon dioxide liquid. The pumping power requirement is very low because you're pumping only a liquid. So the compared to the power consumption of the compressor, the pumping power requirement is maybe at least 1 order of magnitude lower. Okay. So this is the one which I have already mentioned. Instead of using forced circulation, I can directly use natural circulation. Okay, I can directly place the ammonia system at an elevation. And I can keep the carbon dioxide heat exchanger inside the cold storage. And the circulation will take place because of the buoyancy. Okay. So these kind of systems are very good for small capacity system where you don't have to handle huge refrigeration loads. Okay, and they are low cost because I'm not using any pump. The problem is the pump has to handle very high pressures. So this is one issue with carbon dioxide pump. Of course, they are available, but if you can avoid them, that will be nice. So in that way, this is better than the forced circulation type. Okay. So we have made a small comparison between a small system of 30-ton capacity. What happens if I'm using in place of ammonia? Suppose ammonia is toxic. So I want to use a safe refrigerant in place of ammonia. If I'm using just arbitrarily, we have selected a low GWP working fluid, that is R1234YF. If I'm using R1234YF for the same capacity and same operating temperatures, what happens as I'm varying the temperature? Okay, so you can see that the power consumption of ammonia is much smaller over the entire temperature range in comparison to 1234. So this is a big advantage, as I already mentioned, with ammonia. It's very efficient. But now instead of using ammonia directly, if I'm introducing the secondary loop with carbon dioxide as a loop fluid, you can see that there is a small penalty in terms of higher power consumption. This power consumption is because of the pump, right? But you can see that even with the pump, the power consumption of the ammonia carbon dioxide hybrid or ammonia carbon dioxide primary secondary system is still much smaller than the R1234YF system. Right? So that means instead of going for R1234YF, we can as well use ammonia carbon dioxide system so that we can make the system efficient, and at the same time we can also make it safe. So these are the typical comparisons between different cycles for the same conditions that are mentioned here for 30-ton cooling capacity and 2 degree centigrade space temperature and 35 degree ambient temperature, etc. And these are the temperature differences considered for heat transfer and the pressure difference, pressure drop for the secondary fluid on the CO2 side if I'm using a forced circulation. Okay, and you can see that this is the comparison. Obviously, the base ammonia system, base cycle gives the best performance. It consumes about 34.5 kilowatt. So in comparison to that, you can see how the other refrigerants perform. And if I'm introducing a cascade, then there is a small power increase. Cascade means 2 vapor compression systems, as I mentioned. So here you can see that compared to the base cycle, there is a small increase in the power consumption. So cascade systems are excellent systems. So wherever we can use, I think they're very good. So if I am comparing that with the natural circulation loop based secondary fluid system, again you can see that this this is consuming slightly more power compared to cascade. And it is consuming about 2 kilowatt and about 6-7% compared to the base ammonia cycle. Okay, so this small penalty that we pay. But as I mentioned, these calculations did not take into account the amount of ammonia used and the reduced pipeline sizes on the ammonia side and all. So the actual difference can be much lower. Okay, so the idea is just to show that we have, instead of jumping to other synthetic refrigerants, we can think of this kind of a hybrid cycles where we are using natural refrigerants and we are not really incurring any heavy penalty. Okay. Now comes the funded project. So this proposal, based on our experience in handling carbon dioxide in all kinds of loops and over different temperature ranges, etc., we thought of developing a small cold storage, ammonia-based cold storage using carbon dioxide as a secondary loop. So we submitted this proposal, and the proposal was supported by ISHRAE. And this proposal was approved by DST, and it's jointly funded by ISHRAE and DST. So it is a 3-year project, and this project is we have successfully completed this. So these are the project objectives. Because of the cost constraints, the project budgetary constraints, we could not propose a very large capacity system. So we proposed a very small 5,000 MT system, cold storage with a 1.5 TR cooling capacity, using ammonia as the primary refrigerant and CO2 as the secondary refrigerant. And obviously, a lot of because we have to develop the complete system simulation model before we design the system. So one of the major objective of this project was to develop accurate mathematical models, both steady state as well as transient, which can be used for design and simulation. And then using these models, you simulate the system performance and the different operational characteristics. And then based on these mathematical models, design and develop the actual system. So these are the major objectives, and the deliverables are mathematical models and computer codes, which can be used for the design and analysis of these systems. And a fully instrumented cold storage of 1.5 TR capacity, which can be used for storing 5,000 kg products. Okay, so the cold storage is designed for this volume, and develop a design and operation guide for this kind of systems, so that if anybody wants to develop these things, the guide can be handy. Anyway, this is adapted methodology. I think we don't have to look at that. So before again to building the system, we wanted to confirm what exactly we are looking at, what we are losing in terms of the power consumption, etc. So using the thermodynamic and simulation models, we have just compared the single stage, the conventional ammonia system for this 1.5 TR capacity. And from our calculations, we found that if you are trying to maintain the cold storage space at 2 degrees centigrade and the ambient at 35 degrees, your power consumption with ammonia is about 1.71 kilowatt. But if I'm using the natural circulation loop along with ammonia system, the power consumption increases to about 1.83 kilowatt. So that means there is a about 0.12 kilowatt increase in the power consumption because of the introduction of the secondary loop. But most importantly, from our calculations, we found that the amount of refrigerant reduced, amount of ammonia used can be reduced to a great extent. Literature shows that if we are using the conventional ammonia type refrigerant systems, the refrigerant charge, that means the amount of ammonia required per ton of refrigeration, can vary widely, at least by 1 order of magnitude. So studies show that it can be as low as 1.4 kg per ton to about 13 kg per ton. Okay, so this is based on a large amount of systems, etc. Okay, nowadays studies show that this 1.4 ton can 1.4 kg can be reduced further by using other systems. But this is what we found for typical single stage conventional ammonia systems. But if you are using a secondary fluid natural circulation type system with two-phase carbon dioxide, that is the proposed system, our initial calculations show that the amount of ammonia can be reduced to almost 0.6 to 0.7 kilogram per ton. So this classifies this as the so-called low ammonia charge systems. Okay. So this is the major advantage. You have to compare this advantage as against the small increase in the power consumption of about 0.12 kilowatt or about 7 to 8% power consumption. Okay, so this was the based on the theoretical calculations. So from the actual studies, we have to see what exactly is the difference in terms of the power consumption and what exactly is the difference in terms of the amount of ammonia used. Okay, so from these base calculations, we were somewhat confident that we can develop a feasible system. Okay. So for before we develop the system, we have to develop mathematical models. So this is a simple physical model considered for the developing the mathematical models. We assume that we keep the air cooler or carbon dioxide evaporator directly inside the cold storage in a duct. So and we'll be using a fan for circulating the air over this carbon dioxide evaporator. So as the liquid carbon dioxide flows through this evaporator, it picks up heat and moisture from the air, thereby cooling the cold storage. Okay, and the cold storage is subjected to a certain amount of cooling load. Okay, and the carbon dioxide, as it extracts heat from the air, it becomes a vapor. So the vapor moves up through this riser. The component, the vertical component through which the vapor moves up is called as the riser. So through the riser, the vapor moves up. It can be pure vapor, or it can be mixture of liquid and vapor depending upon the operating conditions. So this vapor or liquid vapor mixture enters into the cascade condenser, where it rejects heat to the ammonia. So the ammonia boils as it picks up heat from the carbon dioxide. Carbon dioxide becomes liquid, and the liquid carbon dioxide flows down through this downcomer. So the vertical components are called as the riser and downcomer. Okay, and we have a cascade condenser where there is heat transfer between ammonia and carbon dioxide, and an air cooler where there is heat transfer between the carbon dioxide and air. So this is the mathematical model, a small direct expansion type ammonia system and a two-phase CO2 loop. So different component models are initially developed, and then all the component models are combined and a complete system simulation model is developed. Okay. So I'm not showing any mathematical equations, etc. So this entire system simulation model is developed in MATLAB platform. So it is solved in MATLAB, and results are generated in MATLAB. A large amount of theoretical results are there, but I'm just showing a typical results. For example, this figure shows what is the operating pressure in the system when I am maintaining the carbon dioxide at minus 2 degrees centigrade. So when carbon dioxide temperature is at minus 2 degrees centigrade, how the pressure varies with power in different points of the loop. Okay, so you can see from this whatever may be the power input, the pressure variation is very small, about 0.4 bar. So that means the circulation takes place with very small pressure difference. This is one big advantage. If the pressure difference is very small, you don't require a very large height. That means you don't really require a big head. Okay, so that is one advantage of carbon dioxide. One major problem with carbon dioxide based systems is this. So please look at this carefully. This green line shows the operating temperature and pressure when the system is operating at a steady state. So if I want to maintain carbon dioxide at about 2 degrees centigrade, and it is in two phase for our system, these results are for our system. The operating pressure is about 32 bar. So you can see that this green line, as I have shown in the previous figure, it's about 32 bar. So this is the pressure at which the entire loop is operating. But due to some reason, the loop is switched off. Okay, or the system is switched off. So once the system is switched off, the entire system will try to reach equilibrium with the surroundings. So if we assume that the surrounding temperature is at 43 degrees centigrade, a worst case scenario, we have a hot surroundings. So surroundings are at 43 degrees centigrade, then you will find that the temperature of carbon dioxide slowly starts rising, right? Since the amount of carbon dioxide is fixed inside the system and the internal volume is also fixed, when the system is switched off, because of this fixed internal volume and fixed mass, as the temperature rises, the pressure starts rising. Okay, so if it is off for sufficiently long time, and if it reaches steady state with the surroundings, you will find that the pressure is almost 80 bar. Okay, so this 80 bar pressure is attained only when the system is off and is its equilibrium with the surroundings, right? So this is what is called as the standstill pressure. That means the system is off, and what is the pressure inside the system, right? So even though the operating pressure is relatively low, that means about 30 bar, my standstill pressure is 80 bar. So this has to be taken kept in mind when we are designing the entire loop. If I am designing the loop for 30 bar, then the loop will fail when the system is switched off because after actual standstill pressure is much higher. So this is a major problem with carbon dioxide based systems, because when the system is off, the pressure can shoot up. So there are many ways by which this pressure shoot up can be taken care of, like using expansion tanks, etc. Okay. But this is something we need to keep in mind. So in our case, what we have done is, even though our operating pressure is about 32 bar, we have designed all the components to withstand the pressure of about 125 bar. So even if it reaches, even if the system is off, and if it reaches the pressure of 80 bar or so, it can still operate without any problem. I mean, there won't be any bursting of the tubes, etc. Okay. And from this figure, we also find that if I want to reduce the standstill pressure, I have to move this line to the left side. Moving the figure to this left side means my specific volume has to be high. Specific volume has to be high means for a given internal volume, I have to use optimum amount of carbon dioxide. I should not use too much amount of carbon dioxide. So it is very important to calculate how much amount of carbon dioxide has to be kept inside the system. That means carbon dioxide charge has to be optimized carefully, so that when the system is off, the pressure doesn't shoot up to very high levels. So this is a point one has to keep in mind when we are designing these systems. Okay. And again, I'm just showing some typical simulation results, because we had to calculate the loop dimensions. What is the height of the loop required, and what are the areas required for heat exchangers and all that. So all the parameters are varied over a practical range. For example, this figure shows what happens to the loop height when I'm varying the diameter. So you can see that when the diameter is low, the required loop height is high. Right? For example, when I'm using a 7.5 mm diameter tube, I require a 5-meter tall loop. Right? But as I'm increasing the diameter, the required loop height will reduce. Okay, so this is because when the diameter is low, your frictional pressure drops will be high. So if when the pressure drops are high, you require a larger head, because you are overcoming the friction only through the gravitational head. Right? So when the frictional pressure drops are high, you need to have a larger head. That means larger, taller loop. Okay. So on the other hand, when I am increasing the diameter, the frictional losses are reducing. So required loop height can be reduced. Right? But reverse this thing is, when I am increasing the diameter, you can see that initially the maximum pressure, that means the standstill pressure, is initially high, but it starts reducing. It reaches a minimum, and again it starts increasing. So my requirement is that I would like to have as short loop as possible, because I want to make the system compact. So I do not want to use very tall loops. So I want to use a short loop to make it compact. At the same time, I do not want to end up with high pressure when the system is switched off. Right? So when I am taking these two factors into account, it means that I have to optimize the diameter. I have to optimize the diameter in such a way that the loop height is not very high. At the same time, the standstill pressure is also not very high, right? So this optimization has to be done using the mathematical models. Okay. Again, when it came to the design of the cascade condenser, remember that we are using a cascade condenser. In the cascade condenser, liquid ammonia will be evaporating, and the two-phase mixture of carbon dioxide will be condensing, right? So we considered two types of cascade condenser. The top one is a shell and tube type condenser, and the bottom one is a shell and coil type condenser. Right? In both cases, as the main aim is to reduce the amount of ammonia used, instead of keeping ammonia on the shell side, we decided to keep the ammonia on the tube side. That means we have gone for some sort of a direct expansion type of evaporator for ammonia. So the ammonia will be flowing through the tubes, and carbon dioxide is on the shell, right? In this case, and if I'm using shell and coil type, ammonia will be flowing through the coils, and carbon dioxide is on the shell. So this has, according to us, this has two advantages. One advantage is by confining ammonia to the tubes, and by going for a direct expansion, the amount of ammonia can be reduced to a large extent. And by keeping carbon dioxide on the shell side, we can actually introduce some additional volume. Thereby, we can reduce the standstill pressure of carbon dioxide. That means, as I mentioned, when the system is off, the pressure rise can be controlled to some extent, because I have some reasonably large volume on the shell side, so that the pressure will not be too high. right? So this is a deviation from normal ammonia systems, where generally ammonia is on the shell side and water or some other thing may be flowing on the tube side. Okay, so in this case, it is reversed. Okay, and we did not know which system is better for us, whether to go for shell and tube or shell and coil type. So again, we have simulated both shell and coil and shell and tube type condensers. Okay, again from the simulations, you can see what is the performance when I am varying the diameter of the carbon dioxide tube. Okay, this is the result. The blue lines are the results for shell and coil, and the red ones are for the shell and tube. So even though the shell and tube appears to be better in terms of the maximum pressure, we ultimately opted for shell and coil because we felt that it is easier to manufacture shell and coil tube, and because of the other practical reasons. So we decided to go for shell and coil. Okay, the final configuration we have gone for the shell and coil. So these are the in our system design, for the system design, these are the parameters we have varied, because remember that we have to optimize the diameter of the carbon dioxide tubes. Okay, so we varied it over a range and then we optimize the diameter, and we have designed the system for 1.5 TR. And for the reasons of avoiding frost, etc., we thought that we'll operate the carbon dioxide at 2 degrees centigrade. That means the cold storage is essentially for storing fresh food. Okay. So the reason why we chose temperature above 0 degrees centigrade is that we wanted to avoid frost formation on the carbon dioxide evaporator, because once the frost forms, the simulation becomes complicated. Okay, we wanted to avoid at least the simulation complications, so we considered temperatures above 0 degrees centigrade. And from our calculations, we find that the operating pressure is about 33 bar, and these are the typical carbon dioxide mass flow rates. Okay, so these are the design parameters, and based on the design parameters, we arrived at the final design values, the optimized values for the system design. So you can see that these are all the total length. Okay, our loop height is around 2 meters, and the total length of the loop is about 28 meters. The total length means it consists of the evaporator length, condenser length, and all that, and all the riser, downcomer, and all. So it's about 28 meters of carbon dioxide tubing. Okay, and these are all the flow rates, masses in each component. So the
Dr.
total mass.
Ramgopal, can I interrupt? Because our platform is only available till 7:30. It will
Okay.
suddenly shut off.
Okay.
So can we?
So how much time I have? Actually, I'm not keeping.
Yeah, we got another 15 minutes more.
Okay, I think I'll be done in another 5 minutes.
Yeah, that would be nice. Thank you.
Okay. So these are all the operating conditions and all. Okay. And then for the ammonia side, these are all the specifications, because we have to condense carbon dioxide, which is at 2 degrees or so. So we have gone for ammonia evaporator temperature of -5 degrees, and we have designed the system for 35 degrees. And cooling capacity is 1.5 TR. So as I mentioned, we have gone for shell and tube type cascade condenser, where ammonia is flowing through the tubes and carbon dioxide on the shell side. Okay, so the condensing unit has typical forced convection type condenser, and all the controls, HPLP cutout, service valves, etc., with all the oil reservoir, oil separator, refrigerant reservoir, and all that. Okay, so these are the specifications of the cold storage compartment. We wanted to store, as I said, 5,000 kilograms of the products. So the internal volume came out to be about 20 meter cube. So based on the insulation thickness, etc., the room size is fixed. Okay, and these are the specifications of the insulation material and the floor, door, etc. Then there is a small observation window. So these are the dimensions of the cold storage. It's about 8 feet by 8 feet and around 11.5 feet in depth. And these are the specifications of the components. This is the carbon dioxide evaporator. This is the fin and tube type evaporator. So since the operating pressures are very high, we wanted to avoid joints. So this is a single inlet, single outlet type. So carbon dioxide, there is no distributors. Okay, carbon dioxide enters through one tube and it flows through the serpentine tubes and goes from one row to the other row, etc., and finally comes out. Okay, from another tube. So this design, the pressure drop is slightly higher, but the advantage is we do not have many joints. So the joints are dangerous because in case of any poor joint, the operating pressures are so high, so there can be problems. So we wanted to avoid that. Again, these are all the specifications of this evaporator, carbon dioxide evaporator. And these are the specifications of the shell and tube type condenser. Okay. Remember that none of these things are off-the-shelf items. We have to design and we have to fabricate. Okay, so they're not available. So we have to design, do the complete system design, complete component design. Okay, so you can see all the details which are required for a shell and tube. So this is a double pass. Ammonia and the passer flows through the tubes. It enters at the bottom and it makes a 180-degree turn and it comes out. So it is a two pass as far as ammonia is concerned. And carbon dioxide vapor enters at the top, condenses, and it comes out at the bottom. Okay, and it is designed in such a way that about 30% of the height of the shell is filled with liquid, and 70% you have the vapor space. Okay, so that you can get good condensation. At the same time, you can get some amount of subcooling on the carbon dioxide side. Again, we wanted to see for the system that we have selected, what are the typical penalty because we are introducing this thing. So these results are from thermodynamic simulation of the entire system. So as I've already mentioned, there is a 5 to 7% penalty in terms of the compressor power because we are moving away from single ammonia system to carbon dioxide plus ammonia systems. But the advantage, you can see that if I'm using a conventional system, my ammonia mass is about 0.9 kg in the evaporator. The total mass is this plus condenser and all that. But if I'm using this cascade system, the mass is reduced from 0.9 kg to about 0.2 kg. So there is a great reduction in the amount of ammonia used. So this is the major benefit. So these are all the specifications and these are all the details of the manufacturers or the suppliers. As I said, most of the things are in-house. The cold storage box is a company here from Kolkata, and the condensing unit is also from Kolkata. We had a lot of difficulty in getting a shell and tube condenser, but we could identify some company in Chennai which could make this. Okay. Initially, we wanted to have very compact condensers for ammonia. So, but unfortunately, because of the budgetary constraint, we could not go for compact ammonia condenser. So we had to settle for fin and tube type ammonia condenser, which actually increased the ammonia mass a bit. Okay. So, but if you have budget, one can think of using the other types of condensers, braze plate, etc., so that you can reduce the ammonia mass further. Okay. And these are all the specifications of the fin and tube evaporator and the manufacturers, right? So these are all the photographs. These are ammonia condensing unit. Okay. So unfortunately, the ammonia condensing unit is not made very compact because of the manufacturing constraint. Because we had to depend on the local manufacturer. So he made it according to his own standards. So we found that the ammonia volume is a little high because he has over-designed the reservoir, oil separator, and all that. So this is something which can be taken care of by redesigning these oil separators and reservoirs. Okay, so this is fin and tube type. This doesn't have the compressor. The compressor will be placed here and other things, fan, etc. So this is the condensing unit after everything is assembled. And this is the CO2 evaporator. You can see that fin and tube type heat exchanger through which CO2 will be flowing and air will be flowing through this. This entire thing is kept inside a duct. So this is the entire schematic of the experimental system because we have to have several valves, instruments, etc. So you can see that this is a cold storage box. We have an evaporator inside, and for measuring the pressure, we had a pressure differential here. And then you can see that we have carbon ammonia mass flow meters, and then thermostatic expansion valves, pressure gauges, HPLP cutout, leak detectors, etc. All the paraphernalia required for a typical refrigeration system. Finally, all the instruments are connected to a data acquisition system so that we can continuously take the data. Okay. In fact, when we wanted to build this system, because it is ammonia, so people are scared. So we did not get space for installing the system. So they gave us space far away from all our departments and all. So it is almost like a forest inside the campus, but it is a forested area where we got some space for installing the system. So you can see this when we have actually made the platform. This is how it was. And then these are all the different development. Then we have installed the cold storage unit. This is the condensing unit. So these are all without before insulation and before any cover. You can see that this is the cascade condenser, which is kept at the top. This is the condensing unit and the cold storage unit where you have the carbon dioxide evaporator. Okay, and again, this is the inside of the cold storage where we have the heat exchanger. We did not keep the duct is assembled later, but you can see the heat exchanger, which is a typical fin and tube type heat exchanger, but a very high pressure operation. Carbon dioxide is spouting through that. This is the pressure differential pressure indicator. Okay, and this is the cold storage box. So this is the final.
Dr. Ramgopal, it's going. I mean, the platform will shut off suddenly at 7:30.
Okay, so this is the my last but one slide. So this is the final system which we have assembled. You can see that the entire system is in assembled fashion. We have operated this system, and there are some issues which we are trying to resolve. So these are all the research highlights from this system. We could successfully build and develop the system.
There are a couple of questions in the question and answer.
Okay, so these are some of the practical problems which we are still grappling with.
Right.
So the still studies are going on, so which we need to take care of. So finally, a large number of people helped us. These are the people who helped us, the funding agencies, our research scholars, staff, etc. Thank you so much for your attention. Thanks for your time.
Yeah, thank you, Dr. Ramgopal. I'm sorry to cut you off like this, but it will abruptly shut. So you won't know what's happened.
No. I mean, I was about to complete anyway. I think it's just in time. So,
yeah.
Please.
So thank you so much, and all the attendees. Please, I mean, this was part funded by DST, and they gave a very excellent report on the project. And I think quickly you can take those few questions from Neeraj Agarwal himself, which whom you know anyway.
Yeah, Neeraj is going to.
Can you see the questions?
No, I think you have to see the captions, is it?
Chart. Q&A. Can you see a Q&A?
Okay. Yeah. Yes. Yes. So one question is from Sheikh Salahuddin. Says properties of pump in ammonia plants and how we arrest the leakage of ammonia since it is very toxic gas. So this is a typical problem with any ammonia system, whether our system or conventional systems. For your information, we are not using any ammonia pump here. So we are using only ammonia compressor. So the leakage has to be arrested. There will be some leakage because the compressor is an open type compressor. So there will be a little bit of leakage through the compressor, but most of the leakages can be arrested through proper welded joints and all. Okay, so but there will be small amount of leakage. Yeah. Second question is from Neeraj. Does the secondary system is more vulnerable for starvation or flooding? Further, higher pressure during off conditions also need to make strong the NH3 tubes. Yeah, you are very right, because the ammonia tubes also will be subjected when the system is pressurized. They'll be subjected to a pressure of 80, 90 bar. So the ammonia tubes also have to be made stronger. But commercially available ammonia tubes, they can withstand this pressure. We didn't have any issue. Okay, and the problem of starvation we really don't anticipate. Because our simulation shows that the fluid is more or less uniformly distributed in the heat source and sink. So as of now, we have not really come across the situation where the evaporator is starved of carbon dioxide. That means all the carbon dioxide is settling in the condenser. That has not happened. Okay.
Can you skip the questions and go to Alok Kumar's question? He is from
okay. He is from Brunel University, London. I would like to know your view of its feasibility and commercialization. Yeah, I mean, see, the only effect of climatic condition is if the outside is hot, then when the system is off, the operating pressures can be high. Only that has to be taken care of through proper system design, internal volume, and all. Otherwise, I don't see any big problem. Okay, so we have to design it for higher pressure. So that is the problem. Okay, I think it is feasible. Of course, copper cannot be used with any ammonia system because we have to go for MSR steel piping, again, just like a conventional system.
Yeah, I think one more, Dr. D.B. Jani.
Yeah, DB Jani, how to control large volume of carbon dioxide of condensation via expansion valve. I think there is some confusion. We don't have any carbon dioxide expansion valve because this is a secondary loop. So we don't have any expansion valve for carbon dioxide. Large volume, we have not really, we have optimized the volume so that the volume is such that the standstill pressure, that means when the system is switched off, the pressure is within the manageable limits. Okay, so that is the thing.
So
But
this a
yeah.
great advantage of ammonia is its solubility in water that can be used to a positive sense rather than it being a villain, you know.
No, I mean, it is
I mean,
used as a positive this thing in vapor absorption systems where we use ammonia as the refrigerant and water as the absorbent.
I'm saying that in the product area also a little bit of leak can be detected by our own
Yes,
nose
yes.
itself.
Yeah, yeah. Even
And
our this thing also we have used for charging and for discharging. When ammonia comes out, it passes through a water bath so that it gets
right,
absorbed in the water.
right, right.
You can also spray water and absorb it, but it's a messy thing. Imagine spraying water in a cold storage
Yeah, that's true.
where a lot
That's
of products are there. Right.
Yeah, so I would say thank you very much because I'm very worried that it will shut off suddenly and then you won't know what happened. So it was very good presentation. You led us actually very sequentially to the final project, which was very nice. And I think some ideas also came up about the domestic refrigerator and the solar water heater. So, I mean,